discoveries in physics, mathematics, chemistry, and other areas, all the way through to technology development, technology applications, and commercialization. Our Institute of Quantum Science and Technology is ahead of its time, as it has fostered quantum research at the University of Calgary for over 20 years. Quantum Horizons Alberta is a program that builds capacity and pursues transformational discoveries in foundational quantum science. We're training the next generation of talent through specialized offerings like our Professional Masters in Quantum Computing, which is one of only few such programs in the world, and our Engineering Physics undergraduate degree with a specialization in quantum. This is a little bit of a sore point for me, though, because I have submitted my resume multiple times to Barry Sanders and to Megan Lee for summer studentships in quantum, and I keep getting turned down. I'm not sure why. Although I did speak to Daniel Oblak coming in, and I'm 6'5", and he said occasionally they have things up on the shelves that they need somebody help to pass. So I'll reach out after Daniel, and you can tell me how much I'll get paid per hour. So silliness aside, in short, at Quantum City, we're building an ecosystem for quantum science and technology in Alberta. And Quantum City as an initiative is narrowing the gap between quantum technology and actually solutions that can support the development of a vibrant economy and scientific hub based in Calgary. And in this regard, Dr. Vukovic's experience and work that she's done is going to be quite relevant. Also, just last thing to mention, just last month we broke ground on QLab, which is a new state-of-the-art facility tied to the Alistair Ross Technology Center, where we already have QHub, which is an ecosystem for convening around quantum. And that is going to support the next generation of quantum technologies and indeed a quantum ecosystem for Calgary. The future is definitely bright at the University of Calgary, and there's more to come. And as Paul has already said, we can consider this a pre-Nobel lecture circuit, this particular lecture. So the pressure's on, Dr. Vukovic. We're going to be following your career on a timestamp from today. Really looking forward to your lecture. Thank you. Enjoy this evening's lecture.
I gave a colloquium yesterday, which was more technical. So for those of you who attended the colloquium, today's lecture will cover some of the other topics to avoid overlap. And it's also a public lecture, so it's more tailored towards general audience. And as you already heard, I will talk about semiconductor quantum systems. As Paul already said, this morning, Nobel Prize was awarded to these three gentlemen, Clark, Devoret, and Martinez, for their work on superconducting quantum circuits. So that's truly remarkable, actually, development, although it was awarded for more of a basic science work. That's really the ground work for all of the superconducting quantum circuits today. And I will today talk about semiconductor quantum systems. What are semiconductors? Semiconductors are really the main ingredient of today's computing hardware, classical computing hardware, information processing hardware. You all know about silicon, but also there are many other semiconductor materials. There is germanium, there is gallium arsenide, indium phosphide. They're used in today's information processing systems, fiber optic communications, in computer chips, and so on. Today, I will actually talk about semiconductor quantum systems that employ some of these semiconductors and also some of the wide bandgap semiconductors. There are other semiconductors, including silicon carbide and diamond, which are wide bandgap semiconductors. And they're used in today's power electronics, for example, in electric cars. But it turns out that they're also useful and important for quantum systems. Right? So they have very similar properties to those other materials that are used in classical computing circuits. And as you already know, there is a lot of excitement regarding quantum technologies. There are different platforms that people are working on, including these superconducting quantum platforms, like the one that today's Nobel laureates are focusing on. There are also atomic physics platforms based on atoms trapped in vacuum and moving them around with lasers. There is a lot of research both in academia and industry on that. And also there are these semiconductor platforms that are leading platforms for quantum networks and also some of the quantum sensors. But as you'll hear in my talk today, we're also looking into using them in different types of quantum systems. And before I tell you really how we are building quantum systems out of semiconductors, I would like to first tell you that photonics is a very important part for all of these different platforms. No matter what your favorite flavor of quantum systems is, for all of these different platforms, you need to use photonics. And for example, for superconducting systems, we need to use photonics in order to interconnect computers and make more powerful quantum networks. And that requires transducers from microwave to optical signals, which are devices that people are developing actively today. For atomic physics systems, we also need different types of photonics, spatial light modulators that are also used in projection displays, but different than those, working at different wavelengths, faster and so on, different switches in order to scale these systems up. And for these semiconductor systems, we also need to build better interfaces to photons so that we can scale up networks beyond state-of-the-art of 3 quantum nodes that people have implemented at Delft in Netherlands. So I will start by telling you how we can make that photonics to enable better quantum systems, and then I will tell you how we can make quantum systems out of these semiconductors like silicon carbide and diamond. So what is photonics? Photonics is really the field where we study guiding and manipulating light on a chip. And these are some images from Synopsys and Intel. There is a lot of work in industry on building photonic circuits for different applications. And some of the applications of interest today, classical photonics applications, are outlined here. You probably know about LiDAR, self-driving cars. A lot of sensors are based on photonics. Augmented reality glasses, right? Meta has a product with Ray-Ban, which are actually augmented reality glasses. They have a display there, but there are also these new generation glasses that will have 70 degrees field of view. And optical interconnects in data centers, right? Optics is already used in data centers to network different computers, but it's going deeper and deeper inside of the computing hardware to connect different GPUs or processors and memory to reduce energy consumption and increase operating speed. And finally, quantum technologies, which is what I will be telling you about. So let's start with one of these applications that you're probably familiar with at some level. There is a lot of interest in AI, right? And we all know that all of the major companies are building data centers, and use of different AI tools is growing really rapidly. And that's driving developments in hardware. As of today, data centers are consuming something on the order of few to 10% of all of the world's electricity, global electricity. And that number is growing rapidly. So within our lifetimes, if something doesn't change, we will be using all of the global electricity on data centers, right? And that's obviously not sustainable. So we need to change something, right? And that change comes at the moment from photonics. So if you look at the Google data center, there are already fibers connecting different servers there, like in this picture. But now we're trying to also connect different GPUs, inside of the NVIDIA hardware or processor and memory, different components inside of the computer using optics. Why are we doing that? Because optical connections should be able to reduce energy consumption while increasing operating speed. Energy of one photon at infrared wavelengths is 0.1 attojoule. At the moment, the best electrical connections in Google's TPUs consume 0.2 picojoules, right, per each transmitted bit. And optical connections that people are making, companies, state-of-the-art connections in companies like AR Labs, are consuming on the order of 5 picojoules per transmitted bit. So that's 7 orders of magnitude greater than energy of a single photon, which means that we should be able to do much better than transmission using electrical currents, right? But we need to do something different. So why are optical connections not at 0.1 attojoule per each transmitted bit of information? It's because photonics is not very good. So if you're looking at a photonic chip today, maybe you didn't see them, you generally see electronic chips. But photonic chips would look something like this. These are pieces of those chips. And they're made by the same foundries that are making electrical circuits. They're not efficient, they're very lossy. As an example, one component that is coupling from a fiber to the chip would basically have a loss that is greater than 50%. So you would throw away more than 50% of your input just because you have these inefficient components. So why are they inefficient? They're inefficient because they're designed manually. We have a fixed library of components that we learn about at school. They fix some parameters, and we never really searched for optimal solutions for different functions. And this is a pressing problem in photonics, in problems like optical interconnects. But in quantum systems, it's even more of a pressing problem because you're transmitting information in individual photons, in individual particles of light. And you cannot afford to lose more than 50% of them. So how do we solve those problems? In my group, we've been working for a long time on something that we call inverse design. So what is inverse design? Inverse design is an approach where you are searching all of the possible solutions to find the optimal one. And the solutions look something like this. They look very non-intuitive, right? They look very different from the ones that I showed you on the previous page. But these are all actually made structures, and they are optimal solutions to different photonics problems, to different problems of mapping light from the input to the output. And I will tell you more about some of them later. You know, they look like abstract paintings, but they actually turn out to be much better than the way we were solving problems before. And they allow you to make better quantum systems, better optical interconnects, and even particle accelerators on a chip, right? You all know about huge accelerators like the ones at CERN. It turns out that you can compact them by using optics and using some of the methods of this type. So how are we doing this? We're doing this by really efficiently searching the full parameter space of all possible solutions. And you may think about this as digitizing this image, and this image is an actual device made out of silicon. You pixelate it, and then you try all the combinations of pixels, which would be all combinations of silicon and air, right? Until you find something that would really split two colors of light like what you see on top left. Or it would really route different channels of light, as you see on top right, where it kind of changes the pattern of light. But how do you search through this huge parameter space? Because it turns out that for every even small device of this type, which is only few micrometers by few micrometers, you can fit 10 of them into a single strand of hair, right? How do you search that parameter space when it's bigger than the number of atoms in observable universe, right? And in that process, we use something that we call inverse design methods, which is very similar to how people are training these artificial intelligence softwares, right? But it is applied to the physical problems. And I'll tell you a little bit about it a little bit later. So let's look at one different problem, right? Let's say you would like to turn a corner for light, right? And if you don't know anything about photonics, you would just be tempted to make a wire, right? And you make it out of silicon or some other material, and you hope that light would make a corner there. But it turns out that, again, you would lose 3/4 of light at that corner if you just make a sharp bend. So doing what you would be doing in semiconductor circuits with wires would not really work very well there. So what do you do instead? Well, you may say, well, I'll make a little bit of a smooth band there, and that will probably work a little bit better. And it turns out that it would work a little bit better. Let me see, hopefully these movies work, because we had to change the computer. Unfortunately, they don't seem to work, but they would be like making corner if it worked. It would work a little bit better, right, but not much better, right? You would still lose 1/5 of all of your light at that corner. So what else can you do? You can make even a larger radius of curvature band, and there you can transmit light with very high efficiency, but it turns out that that would occupy a lot of your chip space. So that's not a very good solution to that problem. So if you actually ask your software to really do this for you, this movie works. It can do it in a very small footprint, right? By efficiently searching through that parameter space, and would design the structure that would, in very small, compact footprint, turn the corner for light and do it very efficiently. So how is it doing it, right? This is, for example, 2 by 2 micrometer space, and it has to find this exact design that would provide this high efficiency transmission. So how do we solve that problem? Even in that 2 micrometer footprint, if you pixelate it into something like 225, 40 nanometer pixels, you would have more degrees of freedom than you would have in observable universe. So you cannot really blindly flip all of the pixels in the structure, because unless you're extremely lucky, in your lifetime you would not find the optimal solution. So what do you do instead? You basically guide your computer software through this humongous parameter space using physics of the problem to find the optimal path to that solution. And that is what we call inverse design. So you can solve this problem in a much shorter amount of time by doing something called gradient descent, right? And if you have taken math and numerical methods, you know about gradient descent. But calculating gradients for these very complex structures is also very tedious and very hard. So instead of manually calculating gradient, we use the trick, which is very similar to backpropagation in machine learning, which allows you to calculate gradients fast. So you need to basically update the structure in every step, but you have to update it in such a way that it makes the maximum influence on the performance of the device. And that is that gradient that tells you how you should travel downhill to arrive at the bottom of the hill the fastest. And to calculate it, you run basically 2 simulations of your structure, what we call forward and backward simulation. And that's exactly how you train neural networks. That's called backpropagation. And from these 2 simulations, you can calculate those gradients that tell you how to update the structure. And that way, you can obtain the full device. Here is another problem where you would like to split 2 colors of light in a very small footprint, order of magnitude smaller than you would normally split it in any photonic structure. And on the right, you see a movie how software travels through that large parameter space and searches for the optimal solution in order to split it efficiently in a footprint that is at least 10 times smaller. And once you obtain the optimal solution, you can take it, fabricate it in a piece of silicon, and you obtain something like this. So these are actual pieces of silicon, 2.8 by 2.8 micrometers. And when you design it, you incorporate minimum feature sizes that you know you can reliably fabricate, right? So this is a block of silicon sitting on an insulator, silicon dioxide, and this structure would efficiently split 2 colors of light, as you would see here, right, in this movie, if it hopefully works. Yes. So as we scan the color of light or wavelength of light, you see that light would initially propagate to the top port, and then it would propagate to the bottom port. And this is something that you can reliably make, but you can also reliably make in commercial foundries, the same ones that would make computer processors or GPUs, and you have to rely on them for high throughput fabrication. So we initially started from these problems of small footprint that we could design easily on the hardware that we had about 20 years ago. Then we moved into fabricating them in 2015. Then we fabricated more complex structures, and all of them look like abstract paintings, but these are actually small pieces of silicon, of semiconductor, etched, carved inside, that are guiding light efficiently. Then 5 years ago, we started making them in commercial foundries. And then a student of mine started a company called Spins Photonics that is actually making or licensing this software and helping commercial users use it for their problems. And now we can solve much better problems, bigger problems, more efficiently. And since we're in Canada, I should say that there has been a big presence of Canadians in my group working on this. My first student, Jesse Liu, who worked on this, you see his name, he's over there, 2013, he's a Canadian. And then Alex Pigot, the first student who demonstrated this inverse design device, is also a Canadian. And I now have a Canadian student, Sydney Mason, who also works on these problems, right? So very, very large presence of Canadian students and postdocs working on this. So going back to optical interconnects, right? The idea is not to have only optical fibers connecting different servers, but have optical connections between the processors and GPUs and processors and memory. And that's really what everyone is working on. Otherwise, we will spend all of the global electricity in the next few decades on data centers, right? So how do we don't go there, right? And one of my colleagues even did the prediction that in several decades following the current growth, not only we will spend all of the global electricity, we would actually need to enclose sun and collect all of the solar power radiated by the sun to power our data centers, right? Which of course is not sustainable, right? So unless we do something, probably in the next few decades we will have, control of when you can watch Netflix or access ChatGPT, because it would not be really possible to sustain the flow and usage of these servers. So we are trying to add photonics to the chips efficiently using these inverse designed circuits. And I know that this looks too complicated, but what you should pay attention to that in addition to all of these wires, which are wires that are used for electrical control, in that box too, we also have an inverse designed element that I will show you in a moment, that complex abstract painting-like structure, which enables us to really pack more channels of communication into the chip and reach these interesting transmission rates and low energies per bit. And that's really the component that does convert how light shape looks at the input to how it looks at the output, so that you can do something called multidimensional transmission. So these are, again, practical devices made by my students and postdocs, and they're also made in commercial foundries. And when you look at the modern photonic or optoelectronic chips, like the ones that maybe would be used to connect different GPUs or processors and memory, this is how they look like. They look complicated. You can't really tell much about what's there. But if you zoom into different regions, there are these abstract painting-like structures that are, again, fabricated by commercial foundries. And again, this is another of these devices. And in these rectangles and zoomed-in regions, there are, again, some of these inverse design devices. I mentioned that we even use this for improving or actually building potentially next generation of accelerators. So it's not just practical applications, it's also used for basic science. And you know about accelerators like LHC at CERN. There is also a linear accelerator at Stanford called SLAC, right? And they all use microwaves or radio frequency waves to accelerate charged particles. And they're generally very long. The one at Stanford is several miles long, and also the one at CERN is huge, humongous. And colleagues of mine at Stanford, primarily Bob Bayer, for many years have dreamt about making them smaller by using optical waves instead of radio frequency waves. If you look at the wavelength, right, how long the wave in optical part of spectrum is relative to radio waves or microwaves, they're much, much shorter. So if you think about the argument that the wavelength of optical waves is 10,000 times smaller, then in principle you should be able to shrink the accelerator by 10,000 times, right? So something that's several miles long, like linear accelerator at Stanford, could potentially be placed on a single chip. But you can't just take accelerator and shrink everything 10,000 times, because it would not really work very well. Metals would absorb optical photons and so on. So instead of this, we have to design new stages of accelerator that would work well for optical frequencies. And that you cannot really do by hand, right? Because you have to find some structure that you can couple light into, and once you couple light, that light for an electron that you would couple here would always provide the kick in the right direction, the same way that particle accelerators do with microwaves. But in this case, this is not a problem that you can solve by hand. People tried to do it for about a decade, that they couldn't do it because it's a complicated problem. But if you ask this same inverse design tool to do it for you, right, for an incoming electron with a particular velocity, it would design something that looks like this. And this is a single stage, and you can stack them together, and when you make it, it would look like this, right? And when you shine light coupled there, it would couple into a pattern that would, for light, that would look like shown on the right. Blue and red are just regions where you have very strong electric field in opposite directions, positive or negative. And for an electron that would go through vacuum, which is this dark black gap there, it would always get a kick in the right direction. And that's really what we demonstrated several years ago. We made this chip in silicon, and we used infrared wavelength photons from a laser, right? And we accelerated an electron in a single stage which is 30 micrometers long. We provided acceleration of 30 mega electron volts per meter. So it's not a very big acceleration, but you can think about it that you can reach mega electron volt within a single chip if you just keep cascading them, right? And you can easily cascade thousands of these stages on a single chip, right? Because people work with very large wafers, semiconductor wafers. And in fact, semiconductor foundry could be making something like this. So why is this interesting? It will never really reach energies that are interesting for modern high energy physics, but it would reach mega electron volt energies. And mega electron volt energies are already used in medicine, in radiation therapies for cancer, right? It could make all of those systems potentially much smaller, right? Just by using light instead of microwaves. And that's indeed the dream, you know, that maybe all of those semiconductor foundries that we're using to make processors, we could use maybe to make new types of accelerators. And maybe every lab or every hospital can have their little accelerator, right, powered with a laser. Maybe radiation treatments would not be restricted to just the best equipped hospitals, because this would be much less expensive than today's commercial radiation treatment tools. So speaking of scalability, right, going back to photonic or quantum systems, all of those photonic applications that I showed you at the beginning, right, they mostly require small footprint, right? If you're building augmented reality glasses, you have to fit a lot of optics into a footprint of your glasses. LiDAR systems, if you've seen self-driving cars, they generally have these large toasters sitting on top of the car with optics, right? And they're not very appealing visually, and there is no fundamental reason why they're so big. You could, in principle, make that much smaller, right, and more appealing. And even for quantum systems, when you see companies marketing their quantum computers inside of black boxes, inside of those black boxes, there is a lot of electronics, there is a lot of lasers, right, a lot of equipment that is used to power those systems. So as part of this process of miniaturizing and enabling new quantum systems, we're also developing new types of lasers, which, as opposed to commercial lasers that sometimes occupy meters of optical table space, could fit on a single chip and be much better and more suitable for these systems. So, for example, we recently put one of those large meter-long lasers, called titanium sapphire lasers, on a single chip. We put an array of those. We're also building other elements of laser systems that are isolating back reflection or stabilizing laser. All of these are very important features, and we're putting them all on the single chip. So what you see, for example, there in the middle is a crystal of titanium sapphire that you would have in that meter-long laser. And what is leaning on it, and on a quarter sitting at the bottom, is our chip, titanium sapphire chip, that has several dozens of those lasers, right? So it's much, much smaller than a crystal that goes into something that is meter-long. It's changing how really people are thinking about this, right? And not only there is a large orders of magnitude reduction in size, there is also a large reduction in cost. Because when you put them on a chip, you don't have operational costs, and also everything is cheaper. Once you use lithography and etching, you can mass produce many of them. So maybe it's also in some way democratizing these technologies, right? Making them available to broader community, because everybody can actually purchase these lasers for $100 instead of paying $150,000 for large tabletop laser. And going forward, we're really working actively on putting them on chip, making them produce pulse light, which is even more interesting, making them more efficient, and making them even cheaper, right? And I'm convinced that some of these technologies will play an important role in scaling of quantum systems that I showed you at the beginning. So going back to quantum systems and quantum technologies, right? I said, well, photonics plays an important role, and I spoke about photonics, right? And photonics is very important for enabling and scaling them further. Photons are ideal carriers of information. Fiber optic communications are based on photons. This is how we're receiving movie signals, at home, internet, and so on. But there are also possible qubits, right? You can make also quantum computers or quantum simulators that are using photons as quantum bits, right? And they're not very good in storing information for a long time, but they're the best possible way of transmitting quantum information. This is why they're essential for building all of these quantum technologies. But apart from building photonics that would enable new types of quantum technologies, we're also building semiconductor quantum systems, right? And of course, all of these enabling technologies that I was talking about are mostly also based on semiconductors, right? Building new lasers is often based on semiconductors. Silicon is a semiconductor that we're using to make a lot of these photonic circuits and so on. We're looking into new materials for making better transducers, switchings from microwave to optical signals. We're trying to make all of these quantum systems, quantum simulators, computers out of wide bandgap semiconductors like silicon carbide and diamond. And we're also making better quantum networks transmitting securely quantum information, again, out of quantum materials like diamond and silicon carbide. So let me zoom into this particular application. Why are we interested in making quantum systems out of this where we already have sizable quantum systems made out of atoms trapped in vacuum or superconducting materials like the today's Nobel Prize? Why is this important? Well, I think it's important because first, we know how to work with semiconductors, right? This is a material that is already used in semiconductor manufacturing. We know how to process it on a large wafers, right? It is more scalable, and systems would be more compact. And you can envision having a chip where you would have all of your lasers and detectors and your quantum system sitting on a single chip, compact chip that could make it into other types of devices, the way we actually put processors and all of the other classical computing hardware into modern devices. So how do these atomic physics-based quantum computers or simulators look like? Here is one example. This is from a work from GILA, right? James Thompson's group in collaboration with Anna Maria Ray. It's, of course, an illustration, but really this is how they look like. There is vacuum, you drop atoms, you trap them there with light, right? You put some mirrors around to trap better light that they're interacting with, and that's how you are doing these operations and simulate other quantum systems, or you are doing some other, potentially, you can map it to other optimization processes or some quantum algorithms that are factoring large numbers or so on. But these systems are very large. Atoms spend limited amount of time there, then you have to reload them. It's not completely perfect, right? And it's not exactly scalable. When you're thinking about this, would you really carry these atoms in vacuum inside of your portable devices? So instead of having this, we're thinking about doing pretty much exactly that, but in a piece of semiconductors called silicon carbide. And silicon carbide is used in power electronics devices. It's a semiconductor that you would find in a lot of electronics in electrical cars. It's also used in fake diamond jewelry because it looks like diamond, but it's much cheaper than diamond. You can get it on wafer scale. And if you have seen Meta Orion glasses advertised earlier this year, the ones that have very large field of view of 70 degrees, they have lenses made out of silicon carbide. They are not sold yet to customers because they would cost more than $10,000. So they're selling cheaper version that instead has glass there. But the ones that are really good are actually having this material inside. And the cost is going down, so it's probably going to make it to the customer in the near future. So we would like to take that material and make that system there. And this is how our current system looks like, right? So what is this? This mushroom is a block of silicon carbide that we're fabricating, manufacturing, so that it traps light efficiently. So instead of those mirrors in vacuum that are trapping light for atomic physics systems, light for us is trapped inside of this mushroom. And it's sitting on a pedestal and on a piece of silicon. And those little balls with arrows, they're representing our quantum bits, which are spins of electrons inside of these impurities in a material. Impurity, I told you this material is silicon carbide. Impurities are intentionally introduced impurities, such as silicon in this particular case, and they act as our quantum bits. So if you're thinking about silicon carbide and diamond, right, you're usually thinking about them as these clear materials without color. But of course, you can buy diamond jewelry in different colors and also fake diamond jewelry in different colors. And that color of jewelry comes from these impurities, like the ones that we're working with, but in much higher concentrations, right? So these are either some dopants, additional nitrogen, or some missing atoms, and so on. And it turns out that those same impurities are very useful for doing quantum information processing. They're used in state-of-the-art quantum networks or quantum sensors, and we also think that they're useful for quantum simulators and quantum computers. So we worked with different types of impurities in diamond and in silicon carbide, but as I mentioned, for silicon carbide, we're literally kicking out individual atoms of silicon, right? And that empty space there is like real atom trapped in vacuum, right? That emptiness is, for us, atom, and then silicon carbide is vacuum, right? And I know it's counterintuitive, but physically it's exactly the same system. And everything is in a block of silicon carbide. You don't need to trap it there, it's there forever. You can make a lot of different structures in silicon carbide. They have very low loss, so these rings and spirals are actually used to guide light there and hold it there for a very long time. It turns out that it's excellent material for processing and guiding light. You can do it with very high quality, you can fabricate these structures so that they have very small surface roughness, 0.3 nanometers, right? So it's a very, very smooth dome that would trap light there and scatter very little light out. And of course, it requires some very precise fabrication and processing. And then we irradiate the structure either with ion beam or electron beam to kick out selectively those silicon atoms, right? So that we produce our quantum bits. How do they talk to each other? They're talking to each other through light that is trapped inside of the resonator. And then we fabricate other structures so that we can probe what's going on inside of the resonator. And this is a real microscope image of another device that is used to probe a resonator that we call the probe. And it looks like optical fiber, if you've seen optical fibers, right? They're pieces of glass, strands of glass, and some people probe these structures with those strands of glass, right? Including many people here, Paul and others in Calgary. We make those strands of glass out of silicon carbide as well, out of fake diamond, and then we remove it from the chip and glue it to the strands of glass, and then we can probe our resonators. Something like this, right? So we bring it closer at low temperature and listen what's going on inside. What is going on inside? Well, this seems like a small system. It has only 10 of these atoms, 10 quantum bits, but it turns out that this system is already difficult to classically simulate, right? Because it's a quantum system that has some imperfections, and all these atoms are talking to each other, right, through optical field. So this movie that you're seeing on the right is a movie of these atoms talking to each other, right? So we're imaging them through that little probe, and we're exciting them with a different laser from top. And each bright spot that you see there is emission from a single atom, right? And again, although the system is small, classically it's already getting hard to simulate. And the best quantum information theorists maybe can simulate this system with up to 20 atoms, right? Not larger than that, which is why we're still working in that regime that they can explain easily. But in principle, in this resonator, a little bit larger than this one, you can already put hundreds of atoms and do the experiment. Except that even if we do experiment, it would be difficult for us to know whether we're seeing something that is correct, because classically, they wouldn't be able to simulate a system of that size, right? And going back to all of that infrastructure that we're developing, like lasers and so on, we're using those little lasers on a chip to probe these systems, as shown here, right? So we're actually bringing that titanium sapphire laser on a chip next to a silicon carbide chip, and we're probing it with the light from there. And you don't need to pay attention to these plots at the bottom, but what is important to know is that the gray pictures come from tabletop laser that costs $150,000. The red and orange pictures are signal from our chip after it's excited with our laser, and the results are exactly the same. And of course, there are many knobs you can turn. You can go back to inverse design, both in diamond and silicon carbide quantum materials. You can also carve out these abstract paintings, which turn out to be more efficient structures. You can also work on precise positioning of these atoms. You saw that they were randomly positioned in the structures in the experiments that we're doing now, because we bombard the whole chip with electron beams. But now we're working on developing the process where we put them at precise positions, right? Which of course you need to do for the future work, and we're working with Sandia National Labs on that. So now atoms are on a regular array, right? We can put electrodes, We know how to do that on silicon carbide because people already make power electronics, and we can control these atoms, shift separation of their energy levels, which is very important to tune them onto each other, but we can also tune material itself and change its resonance. So this structure on top left is, again, a resonator made out of silicon carbide with electrode, right? There are electrodes on a side and one contacting it, and looks like a bridge, right, that is bridging the space around. So that's what you use to do all of this. And finally, in the future, the image of how that circuit would look like is something like this, right? In a single resonator, you can already have 100 qubits, and certainly on a chip, you can make millions of these qubits, right, and connect resonators together because there is a lot of space. People already have 6-inch silicon carbide wafers. One of these resonators is only 12 microns, so you can pack millions of them on a 6-inch wafer and connect them together, right? So there is no limit to scaling. There are no limits like what you have in superconducting systems, how many you can put in single dilution refrigerator, or in atomic physics systems where you can trap only 10,000 atoms inside of one array. And going forward, this recipe of combining new materials, right? And I talked a little bit about several materials that we're working with, but there are many others. Combining it with new design tools, right, is, I believe, the right recipe to build both new technologies, but also new platforms for basic science, because all technologies really start from basic science, right? And with that, I'd like to close, and thank my group, and thank you all for your attention. Thank you very much.
Okay, thank you. Thank you for the excellent talk,
Thank you.
Jelena. We have time for questions. So if you have a question, please put up your hand and I'll bring the mic over to you.
Thank you. I was wondering, with respect to these machine learning designed photonic components that you talked about, do you believe that you're sort of reasonably close to sort of maximum efficiency, or do you think there's a long way that you could still go in terms of making them more efficient?
Yeah, so that's an excellent question. So when we're designing these structures, we set up the target efficiency that we would like to have. And we basically stop when we find that particular efficiency or particular footprint, because those are what we say our figures of merit. Now, speaking of whether this is a local optimum or global optimum, this is always a local optimum. But it doesn't matter that it's local optimum if it's good enough, right? If it reaches figures of merit. For certain problems, like this wavelength splitter, we studied the full parameter space, and it turns out that even in that small footprint, you can find 6 really good local optima, although the footprint is order of magnitude smaller than the way we would be basically solving this problem traditionally, right? So the answer to your question is yes, we know that, we reach the efficiency that we would like to reach. We stop when we are close to 100%, and generally efficiency of all of these devices is over 90% because this is what we need to do. But if we start solving the problem and we see that it is getting stuck in some local optimum, right, that is not good enough, then the solution is to restart the problem, right? They initialize differently and repeat. And from the very beginning, we've been developing this software in such a way that it's much faster than commercial electromagnetic solvers, because you need to solve this problem hundreds of thousands of times until you get to the solution, right? So we're basically doing it on GPUs, the same type of hardware that's used for AI.
Thank you. Thank you.
Hi, I guess it's just a question I have. I know a couple of months ago, China invented the Mercator 1 photonics chip. Do they also use inverse design? Or is this
Nokia or?
Mercator 1 photonics chips? This was a couple months ago, and it came out in the articles. Maybe it was niche, but I was wondering if they also use inverse design or no.
First, inverse design, I don't really know everyone who is using it. I know Google is using it, right, for their data center chips. They had papers. And first, our software, even before company was started, was licensed out of Stanford by many companies and many university groups. Sometimes I know who is using it because they publish papers. Sometimes people don't publish papers. So I know Google, for example, is using, Corning is using, and it's moving more and more into industry. And right now, again, all of the chips that I was showing were fabricated in commercial foundries, the same foundries that make also electronic chips. And obviously, foundries are interested in this because you can solve problems in a much more efficient way than solutions that they offer you in their libraries. Yes.
Awesome.
Okay, more questions? I can ask one.
Yeah, there is a person there. Yeah.
Thank you for your talk. You mentioned that with the current technology, the electricity demand is around 10%.
Yeah.
Do you have an idea how much would be reduced if the technology is changed for
Yeah, that's an
photonics?
excellent question. So, this is something that people have tried to pin down exactly. In 2022, people reported 1 to 2%, and speculations are that now it's about 10%, right? But, of course, people are building new power plants and also trying to reduce energy consumption. We do know that the number that is used for electrical interconnects in data centers, again, they're making electrical interconnects more efficient, but as of a few years ago, the estimate was that that number was on the order of 5% of that. Again, maybe 5 to 10%, but this is not something that's widely reported because it's even hard to pin down how much energy is used in a data center or how much energy consumption there is. And for electrical interconnects, it's hard to get those numbers. So I know the number from Google because they just gave a talk, their leading person for their TPU group, and they said that right now they're at 0.2 picojoules per bit for electrical connections in TPUs, but that number was 5 times larger a few years ago. So they're also making improvements using shorter connections, right? So that's why there is a very large error bar, but it's safe to assume that that number, that's just used for electrical connections in data centers is probably on the order of 1% of all of the global electricity. Yeah.
Thank you for the talk. I'm just interested. The chips, they're quite unique designs. I'm interested to what process do you use to actually fabricate those designs?
Exactly the same process that is used to make any semiconductor processors, right? Just lithography, when we make this design, right, we incorporate whatever constraints there are in the process, whether the minimum feature sizes, minimum distances between holes, what is the material stack that a foundry or what we can make, right? So that's incorporated into design. That's why we call it fabrication constraint design. But then once you produce that pattern from your software, you can export it. And those of you who are maybe working on electron beam lithography, if there are people in the audience, have heard about GDS files, right? So you take that GDS file, which is a product of software, and you send it directly into a foundry or your electron beam lithography system, and you just draw that pattern, right? And again, interesting thing, the reason why these tape outs in foundry are called tape outs is because in the past, when people started making chips, they would send magnetic tapes with their designs, right? So that's why they're still called tape outs, but actually we're not sending tapes, we're sending GDS files, right? So even if you were sending regular designs, it would just be that file, right? And then foundry would use it to make a mask and perform lithography. Yeah.
Perfect. Thank you.
Thank you.
I'm just wondering if you use the inverse design method for cavities, or if there's a need to.
Yes,
design-
that's an excellent question. We did, actually. The first paper that we published, even before that paper that I mentioned in, I think, 2011, so almost now 15 years ago, was designing cavities with inverse design and, trying to maximize photon storage time, minimize volume where light is localized, right? And it did produce a cavity, like resonator, that performs better than the other cavities, but it was really impossible to fabricate, right? So we did publish a paper because it was nice, but it was not practical. And it turns out that if you just lightly design the full cavity, generally it produces something that's not easily fabricable. So what we are doing now is still we're designing cavities, but we're not really designing the full resonator. We're designing mirrors of a resonator to satisfy particular function, either for nonlinear optics or, for those of you who are experts, dispersion and engineering and so on. And it's really good in that, right?
Hi, thanks for your talk. My question is more personalized to you. What, in your opinion, is the next biggest technical hurdle in the face of commercializing this technology?
This particular technology or quantum systems in general?
I'll let you have the freedom to answer.
Yes, and are you asking for everything that I showed today or quantum systems in particular?
Quantum systems specifically, yeah.
Yes, so maybe we should define what commercializing means, right? Because there are already commercial quantum systems, but those commercial quantum systems are still primarily used for research, even the ones that you can access them in the cloud, or some research institutes purchase that atomic physics system, for example, but they're still used for research, right?
That's
for
fair.
basic science.
I suppose in a consumer base.
In a consumer way, right? So that hasn't happened yet. If you're thinking about commercializing it in a sense, in the same way that classical computing hardware has been commercialized, right? I do think that you need changes that we're discussing here, that commercializing in that same way something that's based on superconductors or atomic physics systems is not really doable, right? So it would have to be based on a chip type technology, right? Which is something that you can distribute to people and let them use it, because if someone wants to purchase their own computer, right, would they really purchase a dilution refrigerator with it, right? Or would they really purchase this laser array and trap atoms and restart and reload atoms every few minutes, right? It's not a consumer technology. It's a useful technology, right? And the way I like to see this is the same type of history, you can see in classical computing hardware, when, the first computing devices, right, were based on mechanical switches, right, during the Second World War, and vacuum tubes, right? And then you would have discrete components, transistors, for which Nobel Prize was awarded, right, in 1940s. But they were not really the platform that was useful to make powerful computing hardware that we have today. What had to happen, right? What was the change that happened? 1970s, people figured out how to integrate large number of transistors on a silicon chip. And that's really what enabled what we had today. If we just stuck to vacuum tubes or to discrete transistors, we wouldn't really have powerful computers inside of our cell phones. We wouldn't have GPUs, right? We wouldn't have powerful computing hardware that we have today. So that transition has to happen in quantum science, or quantum science in engineering. And we know how to process semiconductors. We know how to make chips. It doesn't have to be silicon, right? Silicon carbide is not very far. It may be silicon carbide, it may be diamond, maybe something else, but we know how to take a piece of material and to process it and to integrate a lot of components on it, which is why I'm very optimistic about these optically interfaced spins, where qubits are artificial atoms inside of a block of material.
Okay, maybe we'll do one more question, and then.
Thank you. Regarding a last technology, which looks like a mushroom, why do we need to check their correctness through classical simulation?
Why do we need to check correctness? That's an excellent question, but that field of verification, of quantum verification, I think there are theorists in the audience who can tell you much more about it, is an active area of research, right? You're building hardware and you don't really know if it's doing things correctly, right? So you, at least, maybe eventually we will be confident that it is doing things correctly, but right now, there are so many, things that are happening there. We don't even completely understand always the physics of these systems. There are imperfections, and we want to make sure that For these smaller scale systems that we know, right, it is doing what it is supposed to do. Right? So I think the right way to go is really picking problems that you can still classically simulate and confirm on smaller size systems that they're doing things correctly. And then as you scale it up, you will be more confident that you indeed is doing things correctly, right?
So the classical simulation is like giving you the correct answer and then you simulate it through the physical system?
Yes, exactly, yes. It's really verification, right? But, I think we do that all the time, right? In computing hardware also, people, before they go into a factory and NVIDIA makes new processor, they're doing simulation of that processor on a very powerful computer that Cadence Systems has, right? So they actually incorporate all of these transistors there and simulate what it would be doing, right? And it's a very difficult simulation. There is only one tool in the world that can simulate, right? But you want to make sure that it should be doing what it is supposed to do, right?
Okay. So one more? Okay.
So I think that last question was very good. This type of mushroom-looking device that you've shown us seems like a very promising platform for making a commercializable system. And you mentioned that you could have precise control of the position of the defects in this type of system. But what I'm curious about is how could you actually individually operate on qubits and individually couple qubits together to develop that type of system into something that can be used to do larger scale quantum computation?
Yes.
Like, how would you manipulate it?
Yes, that's of course excellent question, and I didn't really explain all the details because this is a public lecture. But kind of like this picture. So how do we operate? This platform allows you to individually address qubits. So again, our qubit is spin of an electron inside of a defect. And we manipulate it with microwaves, right? So these wires that are brought near individual defects are bringing microwaves that are doing spin rotations, right? But they're talking to each other through optical field that's traveling through the resonator. Right? And it turns out that there are a few different optical modes that you can actually use in the system. So you can detune pairs of qubits with electric field, and we know how to do that, to one particular mode. All of the others are detuned. Make them interact through that optical mode that does 2-qubit gate, right? And then tune them back, right? So that's really how we're doing it. And it's not very different from how people are, for example, doing things with atoms, where they're actually picking atoms that they would like to interact with, doing interactions and putting them back. We're not physically moving them, right? We're just detuning them from their interaction channel.
Okay, so thank you very much on that future-looking note. Let's thank Professor Vukovic one more time.
Thank you.
And I'd just like to thank all of you for coming out tonight on Tuesday night, and hopefully we'll see you again, not just in the future public lectures, but we have lots of quantum activities happening both in Nyquist and in Quantum City, so watch out for announcements and hope to see you all again soon. Thank you.
Thank you.